Hello, class! Super exciting topic today. We're going to be getting into the history of the atom, atomic theory of matter. This is section 2.1, and then we'll later touch on 2.2, hopefully in the same video. So, kind of boring, but still you need to know this. So let's get going. First, notice that I have this timeline. I'm going to be gradually adding things to this timeline as we move through these notes. First person on this timeline is Democritus. He was a Greek philosopher, and he was thinking, okay, if I take all the matter in the world and cut it into really small pieces, eventually there will be a size of a piece that I can no longer cut. And he called that the atom, or atomus was the Greek for meaning indivisible or uncuttable. So all matter of the world is made of tiny individual particles that you can't cut any smaller. That was Democritus. Next on our timeline comes John Dalton. Now if you notice, there's a huge gap between these two dates. That's because Aristotle, kind of trivia here, Aristotle came in around a little bit after Democritus and said, hey, we don't actually have elements. We have earth, wind, fire, and water. And a lot of people believed Aristotle instead of Democritus, which is why it took so long to get the atom figured out. John Dalton came along in 1803, though, and he came up with a theory about the atom. So here's Dalton's atomic theory. There are 4 things. They're called postulates as well. But here's Dalton's atomic theory. First, each element is composed of extremely small particles called atoms. And some of these I'm not going to read. I'm just going to summarize. So ultimately, your elements are made of atoms. Then, all the atoms of an element are identical. So all of your atoms for oxygen are identical for all of the oxygen atoms. And all of your element nitrogen has the same atoms, whether it's this atom over here or this atom over here, they're both nitrogen. Now, your third one is that one element's atoms are completely different from another element's atoms. And they're not going to change into each other with a chemical reaction. So one oxygen atom is not going to turn into a nitrogen atom in a chemical reaction. Now, we still have compounds that change, but that's kind of a rearrangement of the atoms. The actual atom does not turn into something different. This is also where we get our conservation of mass. So atoms can neither be created nor destroyed in chemical reactions. We'll come up with that in a moment. His last postulate was that your compounds are formed when different atoms are combining together. So you can have a compound when you've got a nitrogen atom and an oxygen atom combining together. Okay, some important laws that came out of Dalton's theories. First, constant composition. So if you've got a compound, it will be the exact same all the way around. So a common example is water. Whether I have water in Florida or water in California, all of that water is going to be 2 hydrogens and 1 oxygen atom. So the water compound is constant. It has constant composition. Another law that came out of Dalton's postulate is that the law of conservation of mass, kind of talked about this before, but again, your total mass at the beginning of a chemical reaction is the same as the total mass at the end of the chemical reaction. This is a main goal with AP Chemistry. So if you have like multiple choice answers and one of them is not conserving mass, odds are that's not the right answer. So law of conservation of mass, really important. Law of multiple proportions, this is not actually part of Dalton's theory, but it's still a law that we need to obey by for different elements. So multiple proportions, ultimately, if you have elements A and B, and they're forming compounds, and they're forming different compounds, then those different compounds are going to be related with a ratio of the masses. So let me give an example of that weird English. Okay, we know that water is 2 hydrogens and 1 oxygen. And if we were to do an experiment, we may actually come up with 8 grams of oxygen for every 1 gram of hydrogen. Now, water is not the only compound in which oxygen and hydrogen combine together. Another compound is hydrogen peroxide. So if we were to look at hydrogen peroxide and to do an experiment, say we didn't know what the compound formula was, we took hydrogen peroxide and we found that 16.0 grams of our compound was oxygen for every 1 gram of hydrogen. Well, if I'm looking at these two, I've got the same amount of hydrogens, but here in hydrogen peroxide, I've got twice as much oxygen as I do in water. So if I take my compound, H2O, for water, and I put twice as many oxygens, then I get my compound for hydrogen peroxide, which is H2O2. Again, I have twice as many oxygen. It's that whole number ratio dependent on their masses. And when you do have two or more compounds, they are never going to be the same amount of atoms. So we are never going to call H2O2 water because it's not the same ratio of our atoms in our compound. Okay, section 2.2, discovery of the atomic structure, kind of continuing on with some history, a lot of dead white guys. So along came J.J. Thomson, mid-1800s. And he is the one who did the cathode ray tube. He's got the plum pudding model. He also is the one that came up with electrons. So let's talk about that for a moment. Let me move my fancy pretty face. Okay. Electron or cathode rays. Couple details about cathode rays. On the next slide, you'll get what I'm saying verbally in a PowerPoint slide, so you can actually write it down. But let me go through some of... Sorry, it's recording. Let me go through what this means verbally first. So in the mid-1800s, scientists studied electrical discharge through a glass tube of about empty air. So they emptied this tube of all of its air, making a vacuum, and then they put a metal over here. It didn't matter what type of metal, and then connected the metal terminals to some electric current. And when you applied a high voltage to those electrodes, then you started getting radiation, and they called that radiation a cathode ray. That's this little bright green thing here. Now, something about the cathode rays is it's not actually being seen. You can't see the cathode ray. The reason why we can see it in this picture, though, is because they have a fluorescent screen around where that ray is. That kind of down here, the tube contains a fluorescent screen that shows the path of the cathode rays so that we can make those invisible rays more visible for us. And fluorescence just means that it gives off light, which is where that green light is coming from. It's coming from the screen around the ray. With the cathode rays, they will travel from the negative cathode, which is here on the left side, so the negative terminal, to the positive terminal, which we're going to call the anode. And then J.J. Thomson described these cathode rays as a stream of negatively charged particles. So that's why he said it was an electron. He called your electrons negatively charged. Here's kind of another picture as to how we know that. So he took a positive end of a magnet, this would have been the positive end of a magnet, and then put it near the cathode ray, and you could see that the cathode ray went towards the magnet. So it was deflected towards the magnet. That's how we determined that that ray of particles was negatively charged. Just kind of a recap of what I just said verbally. High voltage travels from negative to positive. The rays themselves are not seen, but fluorescence, deflected by a magnet. You could also do an electric field to deflect it. And then it's made of electrons, which are negatively charged. Hopefully you remember that from last year chemistry. Okay. He also did another experiment with your electrons, so a similar cathode ray tube. You've got your cathode and your anode, but he put a hole in this anode so that your particles could go, or your cathode ray electrons could go right through. And then we've, instead of like the whole thing being fluorescent, we have just this little screen over here. Now, what he did with this experiment is he had an electrically charged plate and a magnet that he could change the force of your plates and your magnet. So he ultimately did the electric field in one direction, the magnet in another direction, and then he was able to move it around so that your cathode ray line was still straight. So it went straight from your anode all the way through. And this might be a little confusing, but we're going to see an animation on this, so bear with me through my example. Okay, so your rays are going all the way through, and then he knew the strength of each of these, so he knew how much he was deflecting them by. Using that and a whole bunch of physics, he ultimately came up with a charge to mass ratio, which was 1.76 times 10 to the 8th coulombs per gram. A coulomb is the SI unit of electric charge. So ultimately we've got electrons and they have some amount of charge associated with them. This is the ratio of their charge to their mass. Okay, so then after J.J. Thomson, along came Robert Millikan, kind of about 1900s, sorry, so about 100 years later. He took the work that J.J. Thomson had done with the mass charge ratio, and he actually found the charge of the electron. So J.J. Thomson did the ratio charge to mass. Millikan did actually finding the charge, and then once you had one, you could find the other. So kind of that, so once you've got the charge to mass ratio, once you know one, you can do the other. In his experiment, he looked at oil drops and he made them negatively charged and kind of looked at their gravity. Again, we're going to be doing an animation with this one on Wednesday, but he ultimately calculated the charge to be 1.602 times 10 to the negative 19th coulombs. Once he found the charge an electron had, then he was able to find the mass of an electron. Really, really, really tiny number, but 9.10938. Notice all those significant digits, they actually know it to that precise measurement. Times 10 to the negative 28th grams is how big a electron is, or how heavy it is. Okay, moving right along, kind of before Robert Millikan happened, we've got some radioactivity happening here with Henry Becquerel and Pierre and Marie Curie. So late 1800s, early 1900s, they were doing some radioactivity. We don't have to know radioactivity for our AP chemistry curriculum, but it's important to talk about here because it leads into some other experiments. So radioactivity is the spontaneous emission of high energy radiation by an atom. It's kind of spontaneous. So it releases different subatomic particles that have more energy associated with them. So Ernest Rutherford also came in here with radioactivity in 1910. He found the alpha particle, which was positively charged and really, really heavy. He also found the beta particle, which was negatively charged, similar to an electron, fairly light, and then a gamma ray. So these are the Greek letters for alpha, beta, and gamma. Gamma rays are not actually a particle. It's more of a wave that carries a lot of energy. So ultimately, he could put a radioactive substance in this lead block. The lead block is there to protect the scientists from, radiation poisoning. Here's a slit, so making all this radiation go through a little tiny hole. He's got a plate that is charged so that he can see which particles have no charge. So for example, gamma rays are uncharged because they go straight through. Your alpha rays are attracted to your negative plate. Your beta rays are attracted to your positive plate. Because your alpha rays are so heavy, they don't move as far away. And that's kind of background information for what he later did. So okay, let me talk about this first. Thomson current model is in around 1900, so circa means around, rough estimate. Around 1900, we've got Thomson's plum pudding model, which is a whole bunch of positives surrounded by negative charges or negative electrons that are spread randomly throughout. Now, with Rutherford's radioactivity data, he was able to come up with the gold foil experiment. So here's our radioactive source in this lead block, and we're particularly looking at alpha particles. We've got a beam of alpha particles, and actually my timer is going to cut off in the next 10 seconds. So this is part 1. I'm going to finish this in part 2, talking about the discovery of the nucleus.